And then welcome everybody to the second talk already of the fourth season of the Isogeny Club. Today we have Mingjie from the Université Libre de Bruxelles presenting, continuing on a similar topic as the last time, but now in HD. So SCALLOP-HD, joint work with Antonin and Lorenz. So Mingjie, take it away.
Okay, thanks for the introduction and thanks for having me here. And thanks for everyone that's showing up for this talk. So today I'm going to talk about SCALLOP-HD, group action from two-dimensional isogenies. This is joint work with Antonin and Lorenz. Imagine we are playing an isogeny game where the game goal is to construct a scalable, quantum-safe, effective group action. Let's first understand the two keywords here. EGA, which is a group action, group G acting on a set S that is effective. So what does that mean? That means let's take little g to be a generator of big G, and n to be an integer, and s to be an arbitrary set element. Then we want to be able to compute the action of G to the n acting on the set element S efficiently. Well, this is probably not the most general definition, but this is enough for our purpose. And scalable, it means we can scale the EGA to bigger parameters. More specifically, it means that we are able to generate bigger parameters and we are able to do the pre-computations with respect to the bigger parameters efficiently. Okay, so that's our goal. So let's see what has been achieved so far in isogeny. Usually we take the group to be the ideal class group of an imaginary quadratic order O, acting on the set of O-oriented supersingular elliptic curves defined over Fp squared. Here SOP is the set of such curves. I will assume knowledge of orientations and this action because they have been introduced by Simon in his talk 2 weeks ago. So the first such construction is Seaside from 2018, where the quadratic order is used is the one generated by Frobenius, and set elements are just J invariants of supersingular elliptic curves over Fp. And this is not an EGA, but just one REGA, meaning restricted effective group action. More specifically, it means that we are only able to evaluate the action of ideals of this shape, which is a product of small prime ideals with exponents EIs, also small integers. In 2019, Seaside is turned into an EGA, which is called C-fish, and the order O and set elements used in C-fish is same as those in Seaside. It's now an EGA, so how did they turn this REGA into an EGA? This is the general strategy here. The strategy is divided into two phases, one offline phase and one online phase. For the offline phase, we first compute the class group, the ideal class group corresponding to the imaginary quadratic order. And then we compute the lattice of relations L, which involves solving discrete logarithm in the ideal class group. Then we do a lattice reduction step. And for the online phase, one solves an approximate CVP problem. By doing so, we can write the original group element G to the E to be using another representative, which is the product of small LIs to small powers. So we can compute the class group action evaluation using the ideal on the right-hand side. That will be more efficient. Okay, so that's what's done in C-fish. However, their method cannot really scale to bigger parameters because of the obstacle that's imposed from the class group computation, which takes sub-exponential time classically. To fix this issue, we had SCALLOP, which was proposed in 2023. The quadratic order they use is of a different shape. It's the adjoining f times square root of negative d, where d is a small integer and f is a big prime. And set elements are oriented curves, but now we can no longer omit the orientation because it's not as obvious as Frobenius now. So we have to find the ways to specify it. And this is also an EGA, and this is an EGA using the similar strategy that was laid out in CFISH. Okay, that's a short summary of what has been done so far. And a little more words on scalability. Scalability is important because of the desire to have better quantum security. The security of the constructions I mentioned before all rely on the following problem, which is the vectorization problem. Given two set elements, X and Y, we need to find a group element G such that the two set elements are connected by this group element. Since 2019, a series of papers studied the quantum security of C-side, leaving whether C-side 512 and C-side 1024 achieve NIST level 1 security under debate. So it is desirable to have an efficient isogeny-based EGA at higher security level. In terms of scalability, CFISH was able to scale to C-side 512, and SCALLOP managed to scale to C-side 512 and C-side 1024. Here is a little remark that we model the quantum security of SCALLOP here as that of C-side when the underlying class group have the same size. Since SCALLOP-HD is built on SCALLOP, so let's revisit SCALLOP here. First, the quadratic order used, I have already said, is the adjoining f times square root of negative d. So why it's easy to find a generator of such class groups is because there is a very explicit formula for computing the class number, which is given as the formula here. And the set element, in the previous slides, I said we should specify the orientation. And the way SCALLOP specifies the orientation is by providing 2 points, P and Q. P and Q give rise to the kernel of a generator alpha of O of norm L1 squared times L2, where L1 and L2 are two smooth co-prime integers. So from these 2 points, we recover the kernel, and from the kernel, we recover the orientation. And the group action computation in SCALLOP is a little bit involved. By group action computation, I mean that given an ideal and EPQ, we need to find another elliptic curve and 2 more points, E prime, P prime, and Q prime, where P prime, Q prime represent the induced orientation. And this is involved because of the fact that in SCALLOP, they cannot guarantee that the ideals considered has norm co-prime to this big L1 times big L2. So that makes the group action computation algorithm quite complicated. And finally, about scaling behavior of SCALLOP. SCALLOP resolves the scaling difficulty that was caused by computing the class group. However, it's facing a new scaling bottleneck, which is solving discrete log in the ideal class group. You may think that, well, the class number is given here by this very simple formula, and the only requirement on F, which is the conductor, seems to be that it's a prime and it's large enough. So we may try lots of such primes and hope that this integer F minus this Legendre symbol is power smooth. Then we should be able to solve discrete log very efficiently. This is not true for scallop because there is another constraint on F that's hidden in finding a generator alpha of O of norm L1 squared times L2. We in Scallop, they try lots of F to first make sure one can find such a generator alpha. So there is not much control on the group size. And therefore, it takes sub-exponential time for Scallop to compute discrete log in this ideal class group. So that's their scaling bottleneck. Ever since the attacks on SIDH since the summer of 2022, the word HD, which stands for high dimension, is getting more and more popular in isogeny-based cryptography. It all starts with this lemma here. Let phi prime be A isogenies and psi prime be B isogenies for integers AB that satisfy the commutative diagram. Let us define F from E2 times E1 prime to E1 times E2 prime by this matrix form. Then F is a D isogeny between abelian surfaces with D equal to A plus B. If we further have that kernel of phi intersects kernel of psi trivially, then the kernel of F is given by the following formula. Essentially, we need to be able to evaluate phi and psi on D torsion of this curve E1. This lemma introduces a new way to represent isogenies. Instead of like giving its kernel explicitly, which can sometimes be hard when the degree of this isogeny, say, is a large prime, we can actually give the kernel of this isogeny between abelian surfaces instead. And knowing the kernel of F, we can be able to compute F, and then we will be able to recover these four isogenies appear in this diagram. That way we also, for example, recover this isogeny phi here. So that's a new way of representing isogeny. A natural question that arises realizing there is a new way of representing isogeny is that can we use this new way of representing orientation, new way of representing isogeny to give a better representation of orientations that's used in Scallop? The answer is yes, and this leads to several improvements over Scallop. Before I continue, I would like to say some tiny remarks. First, representing an O orientation iota on E, sorry, is equivalent to representing an endomorphism theta in the image of O such that this theta is isomorphic to O. And also representing an endomorphism theta in the endomorphism ring of E is equivalent to representing the Z theta orientation on E induced by theta. So from now on, I will use the phrase representing an orientation and representing an endomorphism interchangeably. Now we define a new orientation and endomorphism representation specifically for our task, which is to represent the quadratic order. Let O be an imaginary quadratic order with discriminant dO. Given an O-oriented supersingular elliptic curves E iota, take any omega in O such that O equals to Z omega, which means omega is a generator of O, and we define omega sub E to be the image of omega under iota, which is now an endomorphism on E. Let beta be in O such that norm of beta and norm of omega and norm of beta as to a 2 power, and their norms are co-prime. Let PQ be a basis of the 2 to the E torsion of E. Then this tuple, which are two elements in the quadratic order, PQ, which is the basis of E 2 to the E torsion, omega EP, omega EQ, which is the image points, which are the image points of PQ via omega E, is called a two-dim representation of E iota. Okay, so that's the definition, contains lots of conditions. What can we do with this definition? How do we justify this name? So given a two-dim representation defined as in the previous slide, we immediately have the following isogeny diamond, where all curves involved are the supersingular elliptic curve E, and the horizontal isogenies are omega E, and the vertical isogenies are beta E, where omega E is the image of omega via iota and beta E is the image of beta via iota. Given this isogeny diamond, we have an isogeny F from E squared to E squared given by this matrix as before. And if kernel of omega E intersect kernel of beta E trivially, which is guaranteed because we have required that their norms are co-prime, then the kernel of F is given by omega E and beta E evaluating on the 2 to the E torsion of E. In fact, we only need to know how omega E acts on the 2 to the E torsion, which is also what we specified in the two-dim representation. We don't need to give the evaluation of beta E on 2 torsion because beta E is also in the quadratic order, so it can be written as a scalar multiplication plus an integer of omega E. So the evaluation of beta E can be recovered by that of omega E. This means that given a two-dim representation, we will be able to recover this isogeny F, and then we will be able to compute this isogeny omega. And by the tiny remarks I said, this means we have a representation for the orientation. That's the definition. So the next question is, can we actually find such representations for quadratic orders? Let O be an imaginary quadratic order of discriminant D congruent to 5 mod 8, then any E iota in SOP admits a two-dim representation. It suffices to show that when E is big enough, we can always find omega beta in O that satisfies the following conditions, which was required in the definition. Let me repeat here. First, omega is a generator, and the norms are co-prime, and the sum of the norms is a 2 power for some E. And let us write down omega and beta explicitly. Computing their norms, we can, and doing some simplification will lead to the following equation, which is equivalent to the equation on the sum of the norms. So we have the following equation. On the left, we have a sum of 2 squares. On the right, we have some integer that involves a variable z. If we are able to solve this equation, if we can find integer solution x, y, z, then we automatically ensure that GCD of norm of omega and norm of beta is 1 because norm of omega is odd when the discriminant satisfies this congruence condition. So all left to do is to actually solve this equation. This equation, the strategy we use to solve this is simply by sampling z from 1 to some fixed bound, and then hope that the right-hand side can be written as a sum of 2 squares, and then we further hope that we can recover x and y as integers. Assuming the following heuristics, which is If Z is sampled as random integers, then the right-hand side behave like random integers of the same size that are either congruent to 1 modulo 4 or equal to 2 times an integer that is congruent to 1 modulo 4. So if we assume this heuristic, then we can show that X, Y can be found in polynomial time quite efficiently. Okay, so that's our algorithm to find 2D representations for an oriented curve. In fact, we can see that the requirement that the sum of the norms is a 2-power is not really essential here. We can simply replace that with another, for example, power smooth integer that is big enough, and we can still solve the norm equations. So that will give more applications in isogeny-based cryptography. For example, this 2D representation outside SCALLOP-HD can be applied in a recent paper by Leroux to provide a new algorithm to perform the during correspondence using isogenies in dimension 2. And it can also be used in the recent anamorphism division algorithm, first appeared in Demiroba's paper in 2022, and then generalized by Merz and Wesolowski in 2023 to replace the isogeny computations in dimension 4 or 8 to computations in dimension 2. Okay, that's the new representation for orientation and anamorphism. And suppose we use this new representation, this 2D representation. We still want to compute our ideal class group action. So how do we proceed? Given the representation and one invertible ideal such that the norm of A is coprimed to 2, then and let phi A to denote the isogeny with kernel EA to calculate the 2D representation for this EA iota A, where EA is the codomain curve and iota A is the induced orientation. We can keep the same omega and beta because we are working with the same quadratic order. And because we assume norm of A and 2 are co-prime, then phi AP, phi AQ also form a basis of the 2 to the E torsion of EA. And then by definition, we know that iota A omega acting on this new basis of the 2 to the E torsion of EA is the following. Here we are really just writing down what is iota A omega by definition. So it's phi A composed with omega E composed with phi A hat, and then divide by the norm of this ideal A. And we can see that phi A hat and phi A cancels out. So the new 2D representation is simply obtained by evaluating phi A on omega EP and omega EQ. So that's a really simple calculation compared with the one in Scallop. Of course, we don't want to use this basis because this may have some leak the torsion points information of the secret isogeny phi A. We can choose another basis RS of the 2 to the E torsion of EA, then the image of iota A omega on these 2 points can be recovered from these 2 points by linear algebra very efficiently. Okay, that's how we move from one 2D representation to another one when they are connected by an ideal. So yeah, now we are ready to present SCALLOP-HD. So the quadratic order we use is the one same as in Scallop, Z adjoining F times square root of negative D. But we have one extra constraint, which is that the discriminant is congruent to 5 modulo 8. And our oriented curves are represented by 2D representation that we just defined. In practice, we can fix omega and beta because our quadratic order is fixed. Moreover, if we use a deterministic algorithm to compute a basis of the 2 to the e torsion of E, then we don't need to always give the 2 torsion basis. So this representation can be given by E plus 2 points, which is same as the shape in scallop. And here are some important parameters for SCALLOP-HD. First, choice of F. Now we don't have that extra constraint as the one Scallop had. So we really only need to make sure F is large, F is a prime, and then we can ensure that this class number is as smooth as possible. And choice of the field characteristic, we want to efficiently represent the orientation. So we require that the 2 to the e torsion is defined over fp squared. And we also want to efficiently compute the group action. So we also want that product of LIs is also defined over fp squared. That in total leads to this shape of field characteristic P. Okay, now that's for parameter choices. And in order to set up SCALLOP-HD group action, we need to generate a starting curve, which is a starting point, a curve and an orientation in SOP, where O is this quadratic order we are interested in. And the way we do this is to compute a descending isogeny phi f of degree f from E0 iota 0 in SOP, where O is now the corresponding maximum order of very small discriminant. To obtain the 2D representation of E iota, we do the following. We first compute an endomorphism phi or a quaternion element, sorry, gamma, not phi, which is of degree phi times 2 to the e over 2 times product of LIs, which is roughly of size p. So gamma in O0 can be found efficiently with full represent integer algorithm, which is introduced in SCALLOP-HD. This first equality is not exactly true. We probably need a small factor here, and that leads to a small exhaustive search step in our algorithm, but that doesn't change the algorithm too much. So once we have found gamma, and since we made sure that the degree of phi is also power smooth, then we will be able to evaluate gamma and evaluate phi on a basis of on the 2 to the e torsion of E0. That will allow us to evaluate phi f on the 2 to the e over 2 torsion of E0. There we have half of the torsion loss because here we have this factor here that we cannot remove. And finally, this implies that we can evaluate omega e on a basis of 2 to the e over 2 torsion of E, which allows us to compute omega e on the basis of the 2 to the e torsion of E by a trick that's introduced in SCALLOP-HD. Sorry, this is the previous paper is not SCALLOP-HD. It's SCALLOP to the 2.0. Okay, that's the algorithm for generating a starting curve. And the remaining steps are the following. Offline phase, we have class group computation, which is efficient. And lattice of relation can be computed in polynomial time since the class group has power smooth order now. And the lattice reduction algorithms remains the same. We cannot do much on this part. For the online phase, the CVP step remains the same. And we have a new formula to compute the class group action. Okay, now we have a small remark on security. Remember that the oriented curve, the starting curve, is generated by connecting it to E0 by a degree f isogeny phi f. A polynomial time quantum algorithm exists to compute the anamorphism ring of E given the evaluation of phi f on points of power smooth order. This is a result from a recent paper joined with Imran, Ivanos, Kutas, Leroux, and Petit. So that means the security of SCALLOP as well as SCALLOP-HD boils down to the following. Can we use the effective orientation omega E reviewed in SCALLOP and SCALLOP-HD to evaluate phi f? Because in this induced orientation, remember the definition of this induced orientation is computed by phi f composed with omega E composed with phi f hat. So of course, there is some information on phi f that's encoded in this orientation omega E. Another remark, which is further discussed if we actually can evaluate phi f using omega E. This is inspired by the FASTA attack paper. It goes as follows. So let N to be a product of split primes in O0, and PQ be two generators of the eigenspaces of omega 0 in the N torsion of E0. There are two independent eigenspaces because we require N to be a product of split primes. And let TS be two generators of eigenspaces of omega E in E, the N torsion of E. The key observation here is that we know the evaluation of phi f on P and Q up to scalars as eigenspaces of omega 0 are mapped to eigenspaces of omega E by phi f. That means the evaluation of phi fp is a scalar multiplication of T, and the evaluation of phi fq is a scalar multiplication of S. So that quite much reminds us of the FASTA setting. So can we apply the FASTA attack in Castrick-Vercautering paper? Our conclusion in the paper is that this is hard because this requires us to find sigma in an anamorphism ring of E0 whose matrix of action on PQ is also diagonal. We have some analysis there, so see our paper for more discussions if you are interested in this direction. Okay, now let's talk a little bit about the implementation and performance. So in terms of scalability, we managed to compute the reduced lattice of relation for discriminant roughly of 4096 bits. But there is an expected issue is that we haven't finished generating a starting curve for 2048 and 4096 due to the lack of sufficiently general genus 2 isogeny libraries. Instead of using the algorithm for set up a starting curve that I just presented in one of the previous slides, we actually use KLPT, which is not so good because we need to work with lots of extension fields. So that means our pre-computation is not completely done yet. even though we have the reduced lattice, but we still don't have the starting curve. However, we believe this shouldn't be an issue with the development maybe of more general genus 2 isogeny libraries in the future. This should become more efficient. So here are some parameter sizes for discriminant up to 4096. We have F, whose bit size is roughly half of the discriminant, and we have N, which is the dimension of the lattice of relation that's used in our algorithm. We actually have several values of N for different discriminants, because there is not an immediate way to see that which N will bring the best performance. So we experimented with several of them. I'm just listing a few examples here. And the field characteristic P is quite large. The other two are to be filled in because, as I said, we don't have a starting curve yet. So so I'm not putting the P's corresponding to those curves here yet. And as for runtime, so for D equals to around 512, SCALLOP runs a single group action for SCALLOP runs in 42 seconds, while ours runs in 88 seconds, but it's a stage mass implementation compared with a C++ implementation. And for the bigger security level 1024, SCALLOP, the group action in SCALLOP takes 15 minutes, and for us, it takes 19 minutes. And we are expecting to have more numbers to be filled in here once we are done with the setup curve algorithm for bigger parameters. Okay, so that brings us to the conclusion. We introduced the notion of two-dim representation for representing orientations and anamorphisms. Besides its application in SCALLOP-HD, this is also interesting in its own right. And we present the SCALLOP-HD group action. Compared with SCALLOP, it has better scalability. The group actions formula is simpler, and the efficiency of SCALLOP-HD can at least compete with that of SCALLOP, as shown by the numbers on the previous slide. And the future work is to improve current implementation of the SCALLOP-HD group action. That's it. Thank you. Any questions?
Thank you very much, Mingjie. As usual, it's just unmuting or typing a question in the chat if anyone has any. Thank you. It was a great talk. Maybe I can start by asking. I mean, this is maybe a bit specific, but do you remember like roughly how, like the vectors once you smooth them, modulo the relation lattice? Like a general group?
I haven't, sorry, I haven't really looked at these vectors.
Okay.
Sorry, yeah.
No, it was very specific.
Yeah, you can probably check it out in the GitHub.
Yeah. There's a GitHub with nice.
Yeah, it's not there yet because we're hoping to like finish everything, but it should be there very soon.
Yeah, makes sense.
There's also a question in the chat by Anders about what takes most of the time in the group action.
What I know is that the two-dimension computation, isogeny computation, actually doesn't take that much amount of time in the group action, but I don't know what is the most. I just know the high dimension computation is actually not that time consuming. Maybe it's some Sage library for isogenies needs to be optimized more. Maybe because the characteristics are so huge. So
and then there's also another question by Supam, if you could reiterate why we need to choose the discriminant as 5 mod 8.
That's because of some theoretical limit that we encountered. I think if we wanted to have a very general condition which is not specific to congruent to 5 mod 8, but then we encounter some issue which is like sometimes the right hand side just cannot be written as sum of two squares for certain congruence relations. So we felt it was a little bit hard to analyze case by case because we need to divide the congruence conditions into many different cases. So we just went for a rather straightforward one. And this one is very easy to analyze and easy to experiment with. Maybe there are more cases where you can apply our algorithm, but it's not as immediate. And for some cases, you cannot have a solution such that the two norms are co-prime. So that will give some challenge for finding the kernel of the higher dimensional isogeny.
I have a related question, which is about so if you mentioned like replacing 2 to the e with a more general integer, would something like that like relax the discriminant condition, or is there also kind of like a when you compute this like genus 2 thing that you have to like that it's just a lot harder with the more general thing? Like, are you using like 2 isogenies or something to compute the higher dimensional isogeny, or is there like...
Yes, that's why we use 2 to the e as the sum of the two norms, right? But in theory, if n is power smooth, then in theory it should also be in polynomial time to perform the high dimensional isogeny computations, but it's just not as efficient for using in SCALLOP-HD.
Excellent, thank you.
Okay. If there are no further questions,
you hear me? I have a few questions.
Yes, of course, go ahead.
Hi. So you mentioned that for isogeny, for the group action, the dim2 isogeny were not the most time consuming, right? So I was curious, do you know about the time for, I think you use pairings for the representation. Do you know the time of pairings?
No, sorry, I didn't look into the details of how the runtime breaks down for our group action computation.
Then you mentioned that you like sufficiently generic pairing isogenies. In practice, which isogeny library do you use currently?
Sorry, can you say that?
Which is the one you are using currently?
The which one? Which is like, I know you're asking which one I'm using, but what's the object that you're talking about?
Yes, which isogeny library are you using?
Isogeny level?
Library code, dimension 2 isogenies.
That's like written by Lorenz, so probably I really just know the result. So
okay. Okay, thanks.
Okay, thank you. Well, if there are no further questions, we can all thank Mingjie again. And then in 2 weeks. Oh, there's okay, there's more questions. Never mind. So Ryan asks, are the keys much bigger there, or is it comparable to Scallop? No, no worries.
I think it.
Oh, sorry.
I think you basically need to compare the field characteristic for us and the ones used in Scallop. So again, I don't know how big their piece are, but if you can compare the two pieces, you probably know the key sizes, how to compare, because it's for both Scallop and Scallop-HD, we have a curve and 2 points.
Then can I ask a follow-up question there? Because can you not express the points as well in this deterministic basis that you had?
This is the image of the 2 basis points, right? So we have to give the 2 images.
Yeah. But why can you not express them as these 2 are a basis for your 2 torsion, 2e torsion? So also the images could be expressed in that basis, right?
Yes.
I think that would make it a bit shorter, because you only need 2 coefficients in 0 to 2 to the e instead of your size of your prime.
2 coefficients or 4 coefficients? You have 2 points and you want to write that as a linear combination of deterministic basis, then.
Yeah, 4. Yeah, I agree. And Pierre actually in the chat says 3 coefficients if you know, and a pairing if you know the degree.
Okay, yeah, makes sense.
And another question is, how is the class group different in this case from Scallop?
The group size is power smooth, but not for Scallop. That's maybe the main difference.
Then now, if you have another question, then you really just need to unmute, because or type very, very quickly, or keep it for after I round off the session. Because I just want to, before we end, I just want to say that in 2 weeks we'll have another session again using Kani's lemma, but now to do pathfinding in the Blue-Hart-Tits tree to compute endomorphism rings of supersingular oblique curves, and it's a talk by Gabriele. So for everybody, so hope to see you all in 2 weeks. And if you still want to hang out a bit, as always, we will keep the Zoom meeting open for a bit to just chat more informally about things.